Everybody, welcome to another episode of Yo at Home. So today we're going to be talking about igneous rocks and how we name them. We're going to be looking at the reference table, so if you have that near you, that would be handy. This is a scheme for igneous rock identification, and want to simplify it here and just talk about, all right, there's two different ways we have of dividing up igneous rocks. One is, do they form near the surface or do they form deep down? So this is just the depth, surface and deep. Why do we care? Well, on the surface you have fast cooling. What does fast cooling do? Makes small crystals. In fact, if it cools so fast, it won't even have any crystals at all. So fast cooling makes small crystals, then slow cooling is going to make large crystals. And that will help us identify it. And you realize right away, if you're seeing small crystals, that rock is telling you about where it formed, what happened to make it form. And when we put it in the context of plate tectonics, it's describing where it formed in terms of plate tectonics. Cool. And similar with large crystals. Large crystals are telling you this rock must have cooled deep underground. All right. So the other thing we have is the composition. Is it felsic? Well, what is felsic? Felsic is high in feldspar and aluminum. Feldspar, aluminum, and silica. All right, aluminum is then the metal that feldspar is using, this feldspar anyway, to bind it together. And of course, silica is the light mineral that mostly makes up quartz and a lot of other rocks that are typical on the surface. So silica is in high abundance, and when we have a rock with a great deal of this, we'd call it a felsic rock. Over here on the dark side, mafic, that stands for magnesium and iron. And magnesium and iron then are dark elements that will make this rock very dark colored. So we have composition going from light colored to dark colored and felsic to mafic, and the depth of formation. So let's start up here. If you have a rock forming near the surface and it's a felsic rock, well, if it forms right at the surface, the options are, if it forms no gas, it's going to form obsidian. And that, of course, is the basaltic or the glassy rock. It basically is just glass. And it will look dark. We have the high mafic composition and the low mafic composition. They're both going to look dark. The reason? A tiny bit of impurity will darken glass very, very much. So you don't need much of a little bit of mafic stuff. So even though this might be technically a felsic composition, that little tiny bits of extra mafic stuff will make this look dark. So obsidian and basaltic glass, very hard to tell the difference between, because they both are glass, they both look dark. If it is gassy, well, this will form pumice, and that's that white stone that you could use to remove calluses and whatnot. White, this is basically a rock foam. Sorry about that. A rock foam. So a rock foam then is a lightweight rock. Some of this even floats in water. That's pumice, right? If it cooled a little bit deeper, so gas pockets cannot form, and it cools slowly enough so glass is not going to happen, because glass only happens if it cools in the space of a few hours. If it cools a little bit deeper, it'll form this beautiful pink rock called rhyolite. Very light rock, light in color, and very small crystals on it. You'll see a few tiny little dark-colored crystals on a pink background of crystals. The pink is all the feldspar stuff. If you look close, you can see some gray crystals, which is the quartz, and then the little dark crystals would be your hornblende and your micas. If it forms very deep, it will cool over a huge amount of time, and the crystals will grow very large, and this, of course, is granite. Granite is the more common of all the igneous rocks. On the continent anyway. Continents are said to pretty much be made of granite. And when we talk plate tectonics in igneous rocks, we'll make that point. So the deeper it is, the larger the crystals. Finally, when you get really deep, you can form a pegmatite, which is just like granite, but now the crystals are becoming huge. Okay? So on the other side, the darker composition, the mafic composition, we would have the same stuff happening at the surface. If it's gassy, it'll form this dark brownish rock called scoria, filled with gas bubbles. Now, this stuff won't float in water, but it's still filled with gas bubbles. And this is the other rock foam. Basaltic glass, as I said, will look very much like obsidian. These things will form usually from volcanoes, where you have rock from the mantle coming directly up to the surface and cools pretty much in a day or so. So scoria and basaltic glass will be the surface situation. If it cools a little bit deeper but still quite fast, you'll have basalt, and that's dark with small crystals. And basalt forms the ocean floor. Yeah, the ocean floor. So there is a huge amount of basalt around, and anytime you have a volcano from a deep spot underground erupting on the Earth's surface, even on land, it'll have a basaltic lava flow. So we'll see these things occasionally. So dark and small crystals. If it forms deeper and takes a longer time to cool, same composition, but now you're going to have dark with large crystals, and that would be your gabbro. And gabbros are on the ocean floor as well, but they would underlie the basalt because they took a much longer time to cool. So let's take a look at the reference tables and compare what we're talking about here. All right, so on this first box here, the environment of formation, inside, outside, intrusive, extrusive, plutonic, meaning formed underground, like the god of the underworld, Pluto, and extrusive, volcanic, erupted at or near the surface. So, going across the top, we have then the composition. Notice composition is here, felsic to mafic. Density, well, the felsic stuff is lower density, the mafic stuff is higher density. The color is lighter to darker, felsic being lighter, mafic being darker. So as we come up here, we can see the rocks actually named. The obsidian still usually appears black, as I said. The pumice is the rock foam. So these are all the things that actually form right near the surface. As soon as you get lower, well, they do have a little class of vesicular rhyolite. Well, that would mean it was close enough to the surface so it cooled fast enough to become rhyolite, so you have some real crystals in it, but it cooled close enough to the surface so gas bubbles could form. This is not very common. Rhyolite also is not terribly common, but is the rock that would have formed fairly quickly, but below the surface so you would have time for rock crystals to grow, for mineral crystals to grow. As you get deeper and you start taking huge amounts of time to form, you have your granites, still a felsic rock, and then pegmatites, as I said. So these really are all made of exactly the same things. If you draw a line straight down here, all of these rocks might have exactly the same composition. The only question is, how fast did they cool? If you extend this line straight down here, it shows you what the minerals are inside the rock and the percentages. Now, an exact mid-composition, you could see about 25% of the minerals in here would be potassium feldspar. From here to about here, or, well, we're looking about 35%, 40% would be quartz. And then from here down, it looks to be about maybe 20% or so plagioclase feldspar, less than 10% biotite mica, less than 10% amphibole. And it can vary based on the composition. So if you had the most felsic possible of these rocks form, you would have then just about 75% potassium feldspar, less than 10% quartz, less than 10% plage, about 5% biotite, and less than 5% amphibole. If you had the most mafic of these that still is able to be called a granite, or rhyolite, or any of these, that would form right along here. And you could see you'd have no potassium feldspar, about 15% quartz. You'd have a huge amount, something about 50% or more plagioclase feldspar. You'd have about 15% biotite mica and about 20% amphibole. So, and these percentages, the way you would read them, is moving across like this. So you could have a composition that reads straight down here, and you'd get the percentages by comparing them here. Okay? In any case, these are the minerals, these are the standard minerals you'd find in a felsic rock. Potassium feldspar, that's the pink to white feldspar. A lot of quartz, not so much plagioclase feldspar, not so much biotite, nor amphibole. On the other side, now we're skipping the middle composition, we'll come back to that, but on the other side, what we were saying, all right, if you draw a line down here, the same thing. These would all have exactly the same composition. The only difference is how fast they cooled. And look at how much plage you'd have. You'd have, it looks like about 35% would be plagioclase feldspar. You'd have in excess of 50% pyroxene. It's a nice green mineral. Then you'd have just a little bit of olivine, just a little bit of amphibole. But if you move over this way, you'd get no plage at all, a huge amount pyroxene, and a huge amount olivine. And that's all you would have. So the compositions change back and forth and would still be able to be called these different rocks. In the middle, you can see there's nothing special about in the middle. It's just not of this, not of this. So what do we mostly have in the middle? Well, we mostly have plagioclase feldspar. You're talking about 60 to 65% plagioclase feldspar in here, about 15, 20% biotite, and about 25% amphibole. So that would be your mid-composition rocks, your andesites or your diorites. Okay? The important part is to put all of this into the overarching scheme of plate tectonics. How does plate tectonics affect your igneous rocks? And how do your igneous rocks tell you what's gone on with plate tectonics? So we'll pick that up in the next lesson.